Okay, so this might be not that hard to believe, but I messed up my audio recording again. It's a problem of trying to run two microphones and two cameras so I can do Zoom and recordings at the same time, because I'm trying not to use the Zoom recordings. They have all kinds of problems associated with them in terms of security. But right now we're working on problem 11A from Mastery Question 0. This is a question about graduated cylinders. So what you may not know is a graduated cylinder is a piece of glassware we use in the laboratory for measuring volumes. This question is particularly about a 100 milliliter graduated cylinder. This is a piece of glassware that is a tall cylinder and has marks every 1 milliliter. And the problem is asking us to find the distance between the 1 milliliter divisions. It's essentially asking us to find the height of a disc that would be 1 milliliter of volume inside the graduated cylinder. So essentially what we have to do is use the information in the problem to find the area of the disc and then figure out what that missing height component is. One of the important definitions that we'll be using in this problem is the fact that 1 milliliter is defined by centimeter cubed. So the concept we're going to use is the area of the circle times the height of the disc will give us our volume of 1 milliliter. Now, we're going to use the definition of 1 milliliter as 1 centimeter cubed. Our height is our unknown, and the area of the circle is pi r cubed. Sorry, pi r squared. You'll notice that the problem, at least in 11a, gives us more information than we need. We've got the inner diameter, outer diameter, and density. Some of that information is for part B. The only piece of information we need here is the inner diameter because the liquids will be inside the cylinder. It gives us as 23 millimeters. To be consistent with the units of centimeters cubed, I convert that to 2.3 centimeters. And then we've got to make sure that we don't use the diameter, but we use the radius. So we're going to use that 2.3 centimeters divided by 2, so we're using radius. We'll go ahead and plug that in, so we'll have pi times 2.3 divided, I made a typo on the screen. That's kind of the benefit of recording over this. I put my units in, I forgot to divide by 2 on the board. I still remember to divide by 2 in my calculator, so I still get the right answer, but what's written on the board is missing a factor of 1/2 squared. So if you do that calculation, you get 2.24 centimeters. The problem asks us for the answer in millimeters, so you go ahead, you get 2.4 millimeters. Again, that's with using the radius, not the diameter. The screen has the diameter up. If you did the calculation that's on the screen right now, you'd get something that's like 0.06 centimeters. You'd get something that's off by a factor of 1/4. Moving on to 11b. This part of the problem is asking us to find the mass of the graduated cylinder in grams. So in order to do this problem, we're going to have to find the total volume of the glass, and then use the fact that we have the density of the glass in order to calculate that mass. So in this problem, we're going to use the inner diameter and the outer diameter. We essentially need to solve for just the glass that's making up that thin rim of the graduated cylinder, that part that I'm coloring in black there, right? That part's the glass that we want to find the mass of. Checking the numbers, making sure it has the right kind of question. After we find that volume of glass in the circle, we're going to turn it into a cylinder by multiplying by the total height of the cylinder for a 100 milliliter cylinder. Recognizing the fact that we've got this mass information, this volume information, we can logically make sense that we're going to be using density. Also in the problem, density is given, and density is that kind of essential connection between mass and volume. This problem gives us, the one that I had gave a density of 2.23 grams per centimeter cubed. Notice we're still using centimeters cubed, so we'll want to make sure we're converting things to centimeters to get that consistency in our units. First, we'll calculate the area of the volume, or the area of the ring, and then we'll multiply by the height for 100 milliliters. So we're going to have the outer diameter, which give us something that's too big. Oh, don't forget the factor of 2. I finally remembered the factor of 2. Outer diameter minus inner diameter, so we just get the volume of that ring. It takes me a moment to plug this all into the calculator. So you should go ahead, if you don't have your calculator out right now, you should go ahead and grab your calculator. This problem is actually one of the only problems that is not randomized because it's actually talking about a real object. So unfortunately, this does just give you the answer to one of your mastery questions, which I don't know how I feel about that, but here's the answer. You should still at least punch it into your calculator. Make sure you know how to use your calculator. The quizzes have a 2-hour time limit from the first time you open it. So you want to make sure that you know how to use your calculator, you know how to find the important equations and everything when you're doing that. So the area of the glass, which is just that ring, is going to be, based on the calculation I did, 0.754 centimeters squared. So now what we have to do is we have to take that ring of glass and we have to translate that across the entire height of the cylinder. In order to do that, we actually need our answer from part A, where we've got our 0.24 centimeters per 1 milliliter. Recognizing that this is centimeters of height per 1 milliliter, not confusing it with the idea of centimeters to volume. So we know our height, we know that this is for a 100 milliliter graduated cylinder. I'll take a moment to point out something funny. An actual graduated cylinder has more glass than the just 100 milliliters. It's got a top to it with a pouring spout, so this calculation is only going to get us in the ballpark of the mass of a graduated cylinder. If it was exactly just the 100 milliliters, you'd get a 24 centimeter height. So we would take our area of ring of glass, we'd multiply by our height, and that will give us the entire cylinder glass volume. Noticing that we've got centimeters squared for that ring area, 24 centimeters for the height, we get centimeters cubed for our volume of glass in the graduated cylinder. We're then going to use that density from earlier, recognizing the unit analysis here. Because we're finding a mass, it's just going to be density times volume. The centimeters cubed will cancel out, and we'll get a nice mass of glass to make a 100 ml graduated cylinder. Don't just skip ahead, use your calculators. I don't know if anyone's going to stand watching these videos with the dub over. 40.3 grams. 40 grams plus or minus a little bit. That's how you do 11B. So here we move on to looking at one of the prep activities for the absorption lab. Particularly, I believe we're looking at absorption prep 2, where there were some people who hadn't yet watched the various videos about this. One of the common mistakes that people make with this prep activity is they try to calculate absorbance when you can actually just copy the absorbance from above in part 2. The part that takes a little bit more work is calculating the molarity for each one of the, I believe it's 7 solutions that you have. So molarity is a unit of concentration. There's a lot of different units for concentration, looking at how much stuff is in a particular volume. But for us, we're going to be using almost exclusively molarity, where molarity is capital M is the symbol we use for it, and it stands for moles of stuff, whether we're looking at atoms or ions or molecules, in a liter of solution. And for us in this class, that'll just be looking at the total volume of the solution, the mix of the interesting thing and water. So you can imagine if you put a bunch of water into a cylinder, there was a little bit of blue dye in that cylinder. This is also a graduated cylinder. If you haven't seen one before, you can see the little blue marks across the side. Those are the milliliter marks. I'm showing the people in Zoom there. And you've got some water that's going to give you the total volume of solution, and there's just a little bit of blue dye in there, which is the interesting stuff. The prep activity has us looking at a yellow dye, and it gives us several different volumes. I'm going to show how to do one calculation for this, but it is actually much easier if you do this in Excel, where you can have it repeat calculations for you very quickly by just changing one value. So the random values I was given was, I was told, you're given a 14.2 micromolar blue dye solution, or sorry, yellow dye solution, and you're trying to figure out what the concentration of that solution is if you took 30 mils of it and you added some amount of water to it to get to 50 mils total. Again, the fact that we have 50 mils total is going to be important in calculating molarity, because the units of molarity is over total volume. So we start with 30 mils of our given stock solution, and then we add enough water to get to 50 mils. In your head, you can say, oh yes, I must have added 20 milliliters. But notice the important thing here is the total volume we end up at, not the amount of water we added. Kind of a chicken and an egg argument there, because you need one to get the other. I said give instead of given. Gotta fix that. So the calculation we're going to be doing is essentially we're going to calculate how many moles of our interesting thing there are in the total volume. The total volume is given, so we've already got that, and we just need to calculate that number of moles. In order to calculate number of moles, we're going to be using that concentration, where we have to recognize that funny symbol there. That's not a U, that is the Greek letter mu, which stands for 10 to the minus 6. So that's going to be 14.2 times 10 to the minus 6 moles of yellow dye molecules per a liter solution, where we are using 30 milliliters. We want our units to match, so we're going to go ahead and convert that 30 milliliters to liters by dividing by 1,000. This will get us the number of moles of yellow dye molecules we must have. After we get that number of yellow dye molecules, just to conceptually think it through, we can say that our eventual molarity is going to be that number of moles that we calculate divided by our total volume, that 50 milliliters, again converted to liters by dividing by 1,000. Get your calculators and calculate. Again, I would encourage you to do this in Excel, because you have to do this calculation 7 times. And Excel is fantastic at repetitive calculations. There's just like a click and drag. If you watch the Excel tutorial, it'll show you how to do these calculations super quick. Now, this is technically a dilution problem. And one of the ways that you can do dilution problems is you can use the equation M1V1 equals M2V2. Your first molarity times your first volume equals your second molarity times your second volume. The reason this works is because we're only adding water. We're not changing the amount of yellow dye. That is to say, the number of moles of yellow dye is still the same. We're just changing the volume and recognizing that the concentration yellow dye per unit of volume must change if we add water to it. I'm going to do this problem in 2 steps still, rather than putting the 2 equations together. So go ahead, grab your calculators and calculate. From this calculation, we get a pretty small number of moles. 4.23 times 10 to the minus 7 makes sense because we have a pretty low concentration. That micromolar is on the order of 10 to the minus 6, so it makes sense. Our eventual concentration will be that number of moles divided by our new total volume by adding some amount of water. And so when we plug that into the calculator, we get a value of 8.52 times 10 to the minus 6, which we can call 8.52 micromolar. Notice our concentration has gone down. That makes sense because we've added water. We're going to end up with less yellow dye per unit of volume. We can also see that it's almost a half-half mixture. 30 mils of yellow dye, 20 mils of water. If it was perfectly half-half, 25 mils of each, we'd get a value of about 7. We've got something that's higher than that because we've got more yellow dye than water. Now, what this problem is really getting us towards thinking about is how we can take multiple measurements of absorbance and concentration and get some physical information about the yellow dye. After we make sure that everyone understands how to do that calculation once, we can go into the conceptual understanding of what we do in part 2 and how that gets us physical information. We have to realize that when we're doing a plot of absorbance versus concentration, this is going to relate to Beer's law. So hopefully you watched the video on Beer's law. If not, I'd strongly encourage you to pause this explanation right now and go look at that video. However, there is some important information that I didn't necessarily go over in Beer's law. The main thing that we recognize is that when we've got a solution interacting with light, there is a linear relationship between concentration and absorbance. The way that we look at that linear relationship is through Beer's law. We're going to have 7 points of data, and this is going to give us some sort of physical information about the chemical, in this case the yellow dye. It's important to realize here that what we do in mathematics is not what we do in chemistry. They're closely related, but when we make these types of plots, it's not just dependent variable versus independent variable. It's actually representing something in the physical world. So in this case, with that linear relationship, and this is something that we just see through observational experimental evidence. We see this linear relationship. We say that absorbance is related to the chemical we're looking at, the path length, how long the light travels through the chemical, and the concentration of the chemical. That epsilon is really important, and again, I strongly encourage you go watch that Beer's law video, the definition of Beer's law. What we are doing here is we are trying to relate this equation that represents some chemical information about how our yellow dye interacts with light to some mathematical information, that is to say, an x-axis and a y-axis. So we can kind of think about how those mathematics map onto this equation we're trying to represent. Our y-axis is absorbance, and so we can make that relationship that the absorbance is on the y-axis. We see that there's this linear relationship. Concentration is on the x-axis. That was a choice. So we can see that there's this direct relationship. If we had a solution that had nothing in it, that was just water, we'd expect the absorbance at 0 concentration to be 0. That is to say, for Beer's law, we can imagine a perfect solution would have an intercept at 0. So we're developing the equation for a line with some slope to our Beer's law equation. We've got our concentration versus absorbance, and if we calculate that slope, it's going to be equal to that last part in Beer's law, the epsilon, the molar absorptivity, times the path length. Path length for us is almost always going to be equal to 1 centimeter, so that's actually a known value. But epsilon is going to have some information about the chemical compound that we're looking at. As absorption changes, there's this linear relationship to concentration, and the tilt of that slope is going to depend on that chemical compound that we're looking at. The next problem we're looking at is Mastery Question Set 1, Problem 4. This is a problem that is related to another aspect of light. And what the question is asking is for the number of moles of photons at a particular wavelength. So we want to make sure that we're analyzing our problem correctly. Moles is just another way of saying a number of photons in a particular units. And it wants to know how many moles of photons we have related to the energy associated with moving a block and a source of light. So there's a lot of different ways that you can approach this problem. The conversation I'm having right now is with somebody in office hours talking about the way they went about solving it. And it's essentially the same way that I'm going to show you in terms of how we think about it. After we identify what the question is asking for, we start to think about what's the explicit information we're given that's going to allow us to solve the problem. Remember, the way that I think about problems is always there's explicit information, implicit information, and the implicit information is the step to get from this explicit information to what the question is asking for. So we've got this, for my numbers in LabPal, we've got this 58.6 kilogram block. It's going to drop 1.74 meters on Earth, which has a gravity of 9.8 meters per second squared. And it even gives us the equation for the energy associated with that. The problem also gives us the wavelength of the light, which is going to have a different energy associated with it. That's our explicit information. We've got to find the piece of information that the problem thinks we can figure out to get to that number of photons. It also gives us this equation, so we don't have to go back and pull out our textbooks in physics. It just tells us we're going to use mass times gravity times height to get the energy associated with the block dropping. And then we're going to relate that energy of the block dropping to the energy of the photon. And this is where that implied information comes from. It's in the absorption background, so we should be looking at the backgrounds. The energy of the photon is h times Planck's constant times frequency, or energy of photon is hc over lambda. Realistically, this problem is something for the end of this week or the beginning of next week, but it's good to start thinking about this stuff earlier than later. Once we get that energy associated with the block dropping, we can relate it to the energy of a single photon and figure out how many photons it takes to get that energy. Plug it into calculator. Being careful about units. Notice we're going to have kilograms, meters squared per second squared. That, with kilograms and meters and seconds, is going to be in units of joules. We go ahead and plug that into our calculator, and we get 999.2 joules of energy associated with the block dropping. We then need to go ahead and calculate how much energy is associated with a photon at this given wavelength of 665 nanometers. get your equation sheet. If you have not been to the modules on the Canvas page, there's some good handouts there. One of them is the equation sheet, which has all of the units we're using and some of the common constants we use. So that's going to be 6.626 times 10 to the negative 34. That's going to have units of joules seconds times 2.99 times 10 to the 8th meters per second, divided by the wavelength, which is 665 times 10 to the minus 9 meters. Notice I pulled a quick switch in there, converting the nanometers to meters, using that Greek prefix to get that times 10 to the minus 9 into meters. The joules, the seconds will cancel out, the meters will cancel out, and that'll give us the energy in terms of joules per a photon. Again, I liked doing it this way. I try to do things where I'm only dealing with one unit at a time. If you do it the other way, there's other ways you can do it that I find more confusing, but if you've got a different way that works better for you, do it that way that works for you. I know the problem on LabPal asks us to find the energy of the photon for a kilojoule per mole. This question, people in office hours were really just asking about the moles of photons. So the way I did my calculation, I kind of skipped that step. I found that the energy per photon was on the order of 10 to the minus 19 kilojoules, 10 to the minus 19 joules. And we'll find whenever we're looking at visible light, we'll always have values that are on that order of 10 to the minus 19 joules. Now, no surprise, we can do a little bit of unit analysis. We want to get the number of photons associated with this. So we're going to take that energy associated with the block. We're going to divide it by the photon energy. So we get photons on top and our number of joules cancels out. And we're going to get a really large number, which shouldn't be surprising because the energy in each photon is really, really small. So to get to almost 1,000 joules of energy, it takes a huge number of photons. I even explicitly write down 10 to the positive 21. In chemistry, we get so used to seeing those negative exponents. I like to write the positive so we know that it wasn't a mistake. I didn't leave off a negative sign. That is a positive 21 photons, a huge, huge number of photons. Now, the problem asks us to put an answer just in terms of number of moles of photons. So we'll go ahead and take that, and using Avogadro's number, which tells us the number of things per photon, and we'll convert from just the number of photons to the units that the problem is asking for, moles. Again, thinking about unit analysis, Avogadro's number is 1 mole per 6.022 times 10 to the 23rd things. Or, you can think about it in terms of the flip if you want things per mole. In this case, that quote-unquote things is going to be a number of photons. But Avogadro's number really works for anything, whether we want to talk about photons, ions, electrons, atoms, molecules, it's a number. So when we go ahead and we do that division, we get something that is 0.00557 moles. We get something that's small when we're looking at it in terms of the number of moles. So then I had a couple students asking me about problems 17 and 18 from the mastery questions. I did that in office hours yesterday, so if you need help with those, I went through the outline of how to do those two problems, but I actually go through those problems completely in office hours yesterday. I was going to post it and do it again without the awkward voiceover for how we do those problems, but clearly I'm working on it. I think I figured out the problem, and it should be better by next time. So here we move on to doing mastery question 0, problem 6. So mastery question 0, problem 6 is asking us to figure out how long it takes for light to travel. This is kind of a physicsy question. The reason here it's in a chemistry class is because it's about unit analysis again, right? In something that's not just chemistry. We call this, in terms of thinking about education, we call this FAR transfer, how two different classes actually relate to each other. So what we're looking at is, again, problem analysis. We've got our given information. We've got a 1 centimeter path length. We've got 3 times 10 to the 8th meters per second. And we want to know, how long does it take? Right? We've got the question it's asking for. We've got the given information. And what we have to do is figure out what that missing piece in between, what the problem assumes we already know, what's implied in the problem for us to figure out. And that's the thing that's missing between the explicit information what's given in the problem and what it's asking for. In this case, it's actually just unit analysis. It's trying to figure out how we can relate distance and speed to a time. So we've got a distance in centimeters. We've got a speed in meters per second. Obviously, we're going to have to be careful about our units. But just in terms of the conceptual, it's going to be distance not times speed, but divided by speed. We want to flip over those units so seconds is on top and meters is on bottom. So that way we get an answer in terms of time. That equation of distance divided by speed goes to time is the thing that the problem assumed we could figure out. After that, it's just a matter of making sure we're careful with our units. So we've got 1 centimeter times the speed, which is 1 meter. Oh, like convert from centimeters to meters so that we don't mess up. 1 meter has 100 centimeters. And then we can multiply by the inverse of speed, which is 1 second is 3 times 10 to the 8th meters. Everything will cancel out nicely, and we'll just be left with something in terms of seconds. Plugging that into our calculator. We get 3.33 times 10 to the minus 11 seconds. And we're not done because, again, we have to pay attention to units. This problem specifically asks us for the time in nanoseconds, not in seconds. So we have to know our Greek prefixes, what that nano means. That is going to be 1 times 10 to the positive 9 nanoseconds for every 1 second. And there's a couple really important prefixes that we're going to be using. It's the kilo, centi, milli, micro, and nano. And I'm going to write those on the board in just a moment because these are important. They're going to come up very often. They're talked about in the textbook, but in terms of ones we use in this class, it's the kilo, the centi, the milli. I think I put 2 L's instead of 1. Micro and nano. Kilo is on the scale of 10 to the 3rd, centis 10 to the minus 2, millis 10 to the minus 3, micros 10 to the minus 6, and nanos 10 to the minus 9. The letters we use for each one are K, C, M, Greek letter mu, and N. Nano is really handy when we're looking at light. Micro is something that we use when we're looking at concentrations of dyes in water. It comes up a couple other places as well. Kilo, centi, and milli. Those are ones that come up pretty often when we're looking at measurements in laboratory settings. So we can go ahead, now that we make sure we've got that information, we can go ahead and do our calculation to get us into nanoseconds. And we get an answer of 0.033 nanoseconds. So it's a very short amount of time, which is not surprising given that light is the fastest thing that exists. The next problem we're going on to here is looking at, I believe it's Mastery Questions 1, Problem 5, which is asking for the molar mass or the natural abundance of different isotopes. To make sense of this, we first have to make sure that we know what an isotope is. So when we're looking at atoms, we've got a nucleus that's going to have protons and neutrons in it, and an electron cloud attracted by those protons. The number of protons is going to define the chemical compound. If we change the number of protons, we change the identity of what we're looking at. We change the reactivity. We change the way it behaves. But if we change the number of neutrons, we actually don't change much besides how much it weighs. So there's this kind of interesting thing that happens in the natural world where we have many objects of various, atoms that have different isotopes. They weigh different amounts even though they have the same chemical reactivity. And if we look at the periodic table, we realize that on the periodic table we're given essentially a weighted average of all of those atoms that exist for each type of compound. So when we look at this, we have to make sense of how we get that weighted average from the things that exist. Now, the nature of why we have different isotopes is beyond the scope of this class. This is looking at Mastery Question Set 1, Problem 5. We have our explicit information, our implicit information. Sorry, the auto zoom is doing terrible things there. So we've got two naturally stable isotopes, chlorine-35 with a mass of 34.968853, and chlorine-37 with a mass of 36.965903. And we want to find the natural abundance. Again, explicit information, implicit information. Takes me a little bit to write that all down. The atomic symbols here, we're using Cl because we're using two things that have the same number of protons, but that number to the superscript left is the total number of protons and neutrons in the nucleus. So those change for the different masses. Both chlorine, because they're the same element, but different isotopes, so they have different masses and different isotopic numbers. It's important in these problems that we actually get the right number of significant figures. These isotope calculation problems actually are subject to quite a bit of rounding error, and so we have to be careful about that. Now, the abundance of each one is kind of unusual that these two things don't exist in the same amounts in the natural world, but that's just a function of nuclear physics, really. It's something kind of beyond the scope of this class. I find it really fascinating and interesting, but science kind of happens in multiple steps. It's kind of, first we see what's happening, then we can start to measure and describe what's happening, and then eventually, hopefully, we get to the point where we actually have some understanding of what's happening. In this class, we're really looking at the measure and describe, at least for this phenomena. So we know that we're going to end up with different abundances for these two things. We can label that as abundance X and abundance Y. And this gets to the point where we've got our inferred information, the information that's missing. Right? Something's missing between the abundances we have, and the abundances we want to find, and the masses that we have. And that missing thing is the equation for essentially doing a weighted average, where we would use the periodic table to get the atomic mass or the molar mass of chlorine, But to make it more interesting, we're using a somewhat randomized number, pretending like we're in a different part of the universe. And so we're going to use the number that's given to us. In this case, it's 35.77968 grams per mole. And that's going to be equal to our abundance of the first compound times, or the first isotope times its mass, plus the abundance of the second isotope times its mass. If this was a perfect 50-50 mixture, we would get something that's perfectly in between. And then we're going to divide by the total abundance of compounds X plus Y. Now, in order to actually solve this, we need more information. We've got an equation with two unknowns, and right now this would be unsolvable. One of the things we have to realize that if we are looking at all of the naturally occurring isotopes, then their abundances add up to 1. All of the chlorine would be 100% of the chlorine. So if we have X and Y as the only two stable isotopes, that would add up to give us the total amount of chlorine in that we're looking at. This would change if we were looking at something that had 3 stable isotopes. You'd have X plus Y plus Z equals 1. But for this case, where we've only got 2 stable isotopes, it's X plus Y equals 1. This gives us a second equation. So now we can essentially do some substitution in order to solve. One thing that's nice is it will allow us to essentially replace that bottom of the equation with just the number 1. And actually, before we do that, we can just do some rational thinking, right? If we look at this, we can say the mass of X is about 35, the mass of Y is about 37, and the measured mass is about 36. We can look at this, and before we touch our calculator and start getting lost in unknown expectations of what an abundance looks like, this looks like it's going to be about a 50-50 mix. 36 is about halfway between 35 and 37. And now the number is a little bit less than 36, so I would actually expect the X to be a little bit larger than the Y, just in terms of what I'm expecting mathematically, and I should expect both of them to be positive. Now let's go ahead and plug in our different values for calculating this. Nice thing is we can just replace that bottom. X plus Y is just equal to 1. We can just plug that in. And then we can go ahead and say, rearrange the equation so that we got Y equals 1 minus X. And then we can substitute in that Y for a 1 minus X. Now at this point, all of our kind of chemistry thinking is done. And we're really just looking at doing algebra at this point. And I was kind of hoping I could skip the algebra. Y'all can do algebra. But I asked people in office hours, I was like, hey, you want me to do the algebra? And pretty much everyone who was in office hours said, yes, we want you to do the algebra. And I was like, okay, we'll do the algebra. So I'm going to go ahead and move that equation out of the way. It's still important, so I'll rewrite it. But I need space to do algebra. So we've got our same mass. Again, we have to be careful with the number of digits we have here. These isotope calculations are subject to rounding error because we're getting things that are like 0.001. So we have to be careful about the number of digits that we carry along. I'm going to carry on as many as I was given in the problem. The 34 is times X, and then I'm going to distribute that into a 36.96, so on and so forth, times minus X, plus the 36.96950 times 1, making sure you've got that negative there. We'll go ahead and subtract the 36.96 over. We'll leave the x's on one side. We'll move the other part over. Both sides are going to end up negative, so we'll end up with a positive abundance. First thing we do, subtract that part over, subtracting 36.9690 from both sides. Gives us a simpler equation. Takes me a moment to use the calculator. Your numbers will be slightly different. This does have some randomized numbers, so make sure you do it for your numbers. The process will be the same, though. Lots of digits. Takes me a while. Negative 1.18622. Negative numbers should make us a little nervous. Almost everything in chemistry, since we're describing the physical world, most things are positive numbers. Mathematically, this works out. The negative just comes from the fact that I substituted y instead of substituting x. You notice we also get a negative 1.99705 there with an x. And then when we do the division, we get our value for x. Which, not surprisingly, as we expected, is pretty close to 50%. Well, actually 60%, but something bigger than 50%. It's not like 99%, it's not like 1%. It's close to 50% and a little bit bigger. So the expectations that we generated before we started punching things into our calculator make sense. We can go ahead and then, using our equation x plus y equals 1, we can calculate what our y value is also going to be. So just 1 minus x gives us about 40%. Right, so about 60%, about 40%. You can see the exact numbers on the screen. The next thing that we went on to was mostly a conceptual question. Somebody asking about the absorption spectroscopy video I did and why things look different colors. So when you look at something that's blue, it actually turns out that it's absorbing in the orange part of the visible spectrum, somewhere around, like the 650 range. This is kind of an interesting difference. I find it one of the most fascinating things about color in chemistry, is the fact that the way we perceive color is not the same as the way the material is interacting with light. So something that appears blue, represented by that blue dotted line there, is actually absorbing orange. So even the blue ink that's on the board there, the blue ink that makes up the plastic of the marker, the light it's absorbing, the way that it's interacting with light, is different than the way that we perceive it. It's not just interacting with blue light, it's interacting with red, yellow, green, blue, and purple. Or it's not interacting, it's really only interacting with the orange light. So the red, yellow, green, blue, and purple light is all making it to our eye, and our brain just goes, let's call that blue. Everything except orange is being reflected off of that blue ink, that blue marker. And that absorption of orange, that complementary absorption, is what gives rise to the apparent blue color. If we looked at something that was red, it's again going to be that complementary green. If that seems really coincidental to you, it's actually the way that the color wheel is made has this kind of complementary aspect of appearance versus absorption built into it, just in the way that we perceive colors and the way that colors interact with each other. So our red looking thing actually doesn't interact with the red light. Red light is being transmitted, but it's actually interacting with just that green light. In this solution, now that it's got the red part and the blue part in it, the apparent red and the apparent blue, it will actually appear purple. This is kind of strange. It's kind of like if you know the art style dottism. This is where you have a bunch of colored dots really close to each other. You got your infrared section over there. That's what I'm talking about right now. But in dottism, essentially, you put two dots so close to each other of different pigments that your brain can't distinguish between the two, and your brain blurs the two dots to make a color. The colors are not actually blended on the canvas. They're just blended in the way that you perceive them. When we mix chemical compounds together, it's like doing that on the atomic scale. This purple-looking solution has blue molecules and it has red molecules, and the molecules are just so close to each other that our brain can't perceive the difference between them. We're not going through some chemical reaction and actually making a purple molecule. We still have blue molecules and red molecules inside that solution. And it's just the way that our brain perceives it. There's a difference between what we see and how the light is actually interacting with the chemical compounds. And what's interesting to us in this class is how the light is actually interacting with the chemical compounds. So someone was asking at this point about what gives rise to an actual purple molecule. And we could imagine that if we wanted a purple molecule, if we wanted a solution that was actually purple, something that was interacting with light in such a way that it appears purple, we would have something that's only interacting with the complementary color to purple, that is to say yellow light. Now, unfortunately, I don't have a purple marker. It would be nice if I had a purple marker. So I actually draw a line in orange, and I start by making a mistake and almost putting my peak in the purple. That's something that would look yellow. And as soon as I did it, I was like, oh, whoops. So I erased that and said, no, we want to be interacting with the complementary color of purple. So we would get something that's actually interacting with that yellow light. If we went and got, the prep activity goes over this to some degree as well, and it actually has a chemical compound that is just purple, and that is potassium permanganate. We could go and get potassium permanganate, and if we dissolved that in water, we would have a solution that only absorbs yellow light and appears purple for that reason. So this gives us two different ways that we can end up with a solution that looks purple. There's actually more than just those two as well. The last problem that we're going to do in this office hours is mastery question set 1, question 2. And this really depends on us being comfortable with some of the material in the textbook and really getting to the definitions of how we look at atoms. Understanding that the general structure is understood to be a nucleus at the center of an electron cloud, where that electron cloud is not actually a circle around the nucleus. It has a lot of different shapes. The spherical electron cloud is just the simplest version of the electron cloud that we have. The nucleus is going to contain protons and neutrons. And so that thing in the middle is the sum of protons and neutrons. We'll often refer to that as the number of nucleons, which is just a fancy way of saying everything in the nucleus. The electrons, the protons, are positively charged entities, and so every proton will attract one electron. And if we have a neutral element, that's to say something that is charged balanced between the protons and neutrons, then the number of protons will be equal to the number of neutrons. But that's only for those cases where we're dealing with neutral elements, things that don't have a charge. If you look at question 2, It actually is a charged ion. So in our case, number of protons will not be equal to number of neutrons. Number of protons will not be equal to number of electrons. So for the symbol that we're looking at, this is an interesting one. It's ruthenium. That 99, that superscript in the top left is the isotope number. That top left number is the number of protons plus the number of neutrons. So we can use that to figure out number of protons, number of neutrons. The symbol, the Ru, those two letters, that is the symbol. That is unique for every element on the periodic table, so it's going to give us the number of protons. The charge in the top right corner, that's going to give us essentially the difference between the number of protons and the number of neutrons. If it was a negative value, we'd have more electrons. If it's a positive value, we have less electrons. Notice we don't change the number of protons because that would change the identity of the element. So I don't expect you to have all of the elements on the periodic table memorized. Go to the Canvas page, go to the modules, download the equation sheet. It has a periodic table on it. It takes me a minute to find ruthenium on the periodic table. It is just below iron, which has symbol Fe because of its Latin name. And ruthenium from the periodic table, I was showing people in Zoom instead of people for the recording. Ruthenium has 44 protons. Having 44 protons in the nucleus defines it as ruthenium. That's why we use that Ru symbol. We can then use that number of nucleons, that 99, which is protons plus neutrons, to figure out the number of neutrons. So I know that 99, 44 plus the number of neutrons equals the number of protons. 44, the number of protons, plus the number of neutrons will equal the isotope number. So we can solve for the number of neutrons by doing a quick subtraction. We get 55 neutrons. The last thing we have to do is we have to figure out the number of electrons. If this was a neutral atom, it would be 44 electrons, because the number of protons and electrons would be equal to each other. All of those pluses, all of those minuses would cancel each other out. In this case, we've got a +3. So we know, since protons are positive, we must have less electrons than protons. We can't change the number of protons. That's what defines it as ruthenium. So we can, I have to give myself a little bit more space, but we can calculate the number of electrons, recognizing that the electrons is going to be equal to the number of protons minus 3. Because I want less electrons than protons, and I want that number less to be the charge. This will make it, again, removing electrons. We can't change the number of protons. Removing electrons, making it so we have 41 electrons, will mean we have 3 more positive charges than negative charges. So we're going to end up with 41 electrons. I have figured out how to do these recordings correctly. So office hours tomorrow, 3 to 5 p.m., we'll have the audio corresponding with live office hours. I don't think I could handle doing another voiceover. It's exhausting. Okay, everyone. See you tomorrow.